All right, guys, welcome to Chapter 8. Chapter 8, we're going to talk about rational functions, and the first of those we're going to look at is inverse variation. We've worked with direct variation, if you remember back to earlier this year, and then also in Algebra 1. And so inverse variation kind of goes along with that, just is a little bit different, okay? So big deal stuff, the essential understanding right here. If a product is constant, a decrease in the value of one factor must accompany an increase in the value of the other, okay? So here's what that looks like. So for direct variation, we used this form. We had this y equals kx, okay? That was direct variation. Inverse variation has the form of xy equals k, or if we solve for y, say we wanted to graph it, we'd have y equals k over x, or if we solve for x, we'd have y equals k over y, as long as k doesn't equal 0. Okay. When two quantities vary inversely, as one increases, one decreases, because what we're saying this, I like this one right here, this xy equals k. Basically, it's an inverse variation if when we multiply the x and y together, we get the same number. So for example, we look right here, identifying whether or not it's a direct or inverse. Here, 2 times 15, 30. 4 times 7.5, 30. 10 times 3, 30. 15 times 2, 30. This is an inverse variation. When we graph it, we get these points right here. Okay, that is an inverse variation. You'll recall that a direct variation was a line. Okay, was just a line. We take a look at this another example here. So a plot of the point suggests that an inverse relationship is possible. Test to see whether the products of x and y. So we just plot it. It looks kind of like an inverse variation. But then if we test it, this is 20, this is 32, this is 30, this is 22.5. That's not an inverse variation. Okay, the products of the x and y have to be the same for it to be an inverse variation. For it to be a direct variation, when we divide y over x, then we get the same. So that's if it's direct. Okay, direct we divide y and x, inverse we multiply. Okay, go ahead and take a second and A, B, and C. Tell me whether or not those are direct, inverse, or neither. Okay, if it is direct or inverse, do me a favor and write a function for the equation. Okay, or for the model. Go ahead and do that now. All right, you've unpaused. Let's take a look at 1A, B, and C. So 1A was direct. This is direct. And the equation there, or the function, would be y equals 40x. Okay. For part B, this was inverse. This was inverse, and you could write y equals 8 over x, or you could have written xy equals 8. Either one of those is fine. And then for part C, this was neither. That was neither of them, so no model there. Okay. Determining an inverse variation. So here, problem number 2 says, suppose x and y vary inversely. So we're telling you, you have an inverse variation. And x is 4 and y is 12. So I know that xy equals 48. Okay, then it says what functions model the inverse variation. So I want to see which one of these, what is the function for that? I just wrote out this part here, right here. We could solve for y and write down 48 over x. Okay, so that's how we do that. We just take the two numbers, multiply them, put them into xy equals 48, and then solve for y. What does the graph look like? That's just plotting points. I'll show you how to do that on your calculator, but sketching it's probably just as easy. And then what is y when x is 10? Well, that's easy enough. You just plug 10 in for the x right there, and y is 4.8 when x is 10. Pretty easy stuff, okay? And very similar to direct variation, which we have some experience with. Let's take a look at got it number 2. Go ahead and try and get some answers to A, B, and C there. Suppose x and y vary inversely, so we're telling you that it's an inverse variation. Give me the function, sketch a graph, and then what is y when x is 2? Go ahead and do that for me now. All right, you're back. For A, hopefully you got y equals negative 56 over x. The graph of this is interesting, and I'm just going to give you a quick sketch of it. There were 2 parts to it. Okay, there were 2 parts. This part right here, and this part right here. And that is just a sketch. Remind me in class to put this in the graphing calculator. You guys could try it. Go ahead and put this in your calculator, see if you get that same image. And then what does the graph of this function look like? Oh, sorry, that was B. What is y when x is 2? So what is y when x is 2? Y is negative 28. Okay? the graph is nice there because it gives you some idea, like obviously when x is 2, that's, here, so y is all the way down here, so I have some idea of what it should look like. Modeling an inverse variation from a word problem. Your math classes decide to pick up litter each weekend in a local park. Each week there's approximately the same amount of litter. The table shows the number of students and the time it took. And then so 3 students, 85 minutes, 5 students, 51, 12, 21, 17, 55, or 17 is 15. So we investigate the data. We look at it and see, does it look like an inverse variation? And so when you plot these points, it does. It looks like an inverse variation. So from the table, NT, or L1, L2, is almost always 255. Here it wasn't. It was 252. Still a pretty good model, though. Okay, still a pretty good model. How many students should there be to complete the project in at most 30 minutes? Well, we just plug 30 in, we solve, and we get 8.5. Since we're not allowed to cut students in half, we would need at least 9 students. Okay, so it's not a perfect model when we have a real-world application problem, but it's pretty close. Okay, go ahead and take a look. This one got it 3 here, and see if you can get some answers for me there. For A, I need the function, and for B, I want to know how many students would I need to clear the debris from an average size yard in about 25 minutes. Go ahead and pause the video and give me some answers there. All right, you're back. Hopefully for A, you got, I used T, since it had a T right there, but you might not have. I used T and N. If you used Y and X, no big deal, but I used T and N. T equals 225 over N. And for part B, I got 9 students. If you aren't getting those, try it again. See if you can find your mistake. If you still can't get them, make sure you make note of it so we can go over those in class. We've seen variation formulas in geometry. Some, like the formula for the perimeter of a square, are simple direct variations. So like as big as, as the sides get bigger, the area gets bigger. Others, like the volume of a cone, have 3 or more variables. So cone, volume, then we're talking about, for a cone, we would have, radius and the height and the slant length. So we have all these different things. When one quantity varies with respect to 2 or more, we have what's called a combined variation. Okay, a combined variation. When one quantity varies directly with 2 or more quantities, we have what's called a joint. Okay, joint variation. The volume of a cone varies jointly with the area of the base and the height of the cone. Okay, so for example, right here, we have more than one variable involved. So combined variation looks like this. Z varies jointly with X and Y. So Z varies jointly with X and Y. Z varies jointly with X and Y and inversely with W. And then we also could have Z varies directly with X and inversely with the product of W and Y. So there's different kinds of combined variations. All right. So how do we use that? Well, right here, for example, the number of bags of grass seed, N, needed to reseed a yard varies directly with the area to be seeded and inversely with the weight of the bag of seed. If it takes 2 3-pound bags to seed an area of 3,600 square feet, how many 3-pound bags will seed 9,000 square feet? Okay, so we have this formula, N equals Ka over W. Okay, they gave us all this information. N equals K, it varies directly with the area, so that's Ka, and then inversely with the W. That's how we know the W goes on the bottom. Then we just plug in the numbers they give us and solve. It's really just that simple. Okay, we plug all this in, we end up getting this for K. Okay, that's now the constant. Okay, the combined variation equation is now N equals A over W, and then this 1 over 600, we just replaced K with 1 over 600. From here, we take in the 3-pound bag, we put it right there, the 9,000 square feet, we put it right there, and we solve. And so we get C. Okay, let's take a look at this practice one. The number of bags of mulch you need to cover a planting area varies jointly with the area to be mulched, and square feet, and depth of mulch in D feet. If you need 10 bags to mulch 120 feet squared to a depth of 3 inches, how many bags do you need to mulch 200 square feet to a depth of 4? Very similar problem, guys. We're just changing seed and stuff like that to mulch, but very similar problem. Go ahead and try and get the setup there, and then tell me, how many bags do you need? All right, you're back. Hopefully for this one, you got 23 bags. Okay, 23 bags. If you didn't, try again using this one right here as your model. If you still don't get it, make sure you make a note of it and we'll go over it in class. So applying a combined variation, gravitational potential energy, PE, which some of you guys might be talking about it if you're in like a physics class, is a measure of energy. PE varies directly with an object's mass and its height above the ground. Physicists use G to represent the constant variation, which is gravity. So we're not doing this in a zero gravity chamber. Skateboarder in the photo has a mass of 58 kilograms and a potential energy of 2273.6 joules. What is the gravitational potential energy of a 65 kilogram skateboarder on the half pipe shown? So what we do is we want to solve, G is 9.8, okay, 9.8. And that's meters per second squared. So then what we do here is we're going to plug in 9.8 and then the information about the new skateboarder. So 65, and then it tells us in the picture right here, guys, the height is 4. Okay, so we plug that all in, and we find the potential energy of that skateboarder. So you know that maybe for skateboarding here, this guy's got 2548 of potential energy. This guy's got 2273. So evidently, bigger skateboarders are better. How much potential energy would a 41 kilogram diver have standing on a 10-meter diving platform? Okay, and so again, similar problem, but instead of skateboarder and 4-meter half pipe, it's a diver. And it's a 10-meter diving platform. And then some reasoning question about an 80 kilogram diver stands on a 6-meter diving platform. At what height should a 40 kilogram diver stand to have an equal potential energy? Go ahead and try and do your best. I think 5B is a tough question, but I think you can do it. Go ahead and try those now. All right, so the answer here for 5A is 4018, 4,018 joules. For part B, the answer is 12 meters. And then after that, no, you don't need to calculate P to find the height. All you have to do is substitute the mass and the height of the first diver and the mass of the second diver in P equals mgh. Set the two quantities equal and calculate the height of the second diver. Solve the equation for h. So that's just solving a system. If you didn't get those, I understand that's not easy stuff. So make sure you make a note of it, and we'll go over it in class. Please, guys, share the video with your friends. It's really important. This unit is difficult, and we want to start it off on the right foot. So go ahead and share this with friends. Tweet it, like it. I don't know. Add it to your linked profile. I don't know what you're doing. But find a way. Make sure everybody's seeing this before class. See you guys next time. Bye.